Hi, today we will present our statistical analysis of NFL player profiles and contracts. Our study looks into how age and salary are distributed among NFL players and whether these factors show patterns that can help teams make better decisions. Since the NFL uses a salary cap system, teams have limited money and must spend it carefully. By using statistical methods, we analyze player characteristics and contract structures to better understand this financial environment. Throughout this presentation, we will share our key findings. Before we dive into the analysis, let's look at our dataset and variables. Our data comes from Kaggle and includes information on 2,846 professional NFL players. Because this dataset doesn't include every single player, we treated it as a sample. We focused on two continuous variables, player age representing experience and maturity, and annual salary measured as the cap hit in US dollars. Our main goal is to find statistical patterns that explain how teams distribute their money under salary cap restrictions. Now let's examine the descriptive statistics. Starting with age, the average age is 25.59 years, while the median is 25 years. Since these numbers are very close, the distribution is almost perfectly symmetric, with a narrow standard deviation of only 2.9 years. For salary, the results are completely different. The average salary is $2.72 million, but the median is only $1.05 million. This large difference shows a strong positive skew, and the extremely high standard deviation points to major inequality in player earnings. In short, age remains stable across the league, while salaries vary dramatically. Frequency distributions. This slide looks closer at the shapes of these distributions. For age, the distribution is mostly symmetric and peaks between the ages of 24 and 27, with the middle 50% of players fitting into a very tight age gap. Salary behaves much differently because more than 88% of players earn less than $5 million a year. Only a small group of elite contracts create the extremely high values we see, looking like a power law distribution where a few individuals receive a massive share of the total rewards.
Next, we analyze outliers using two different methods. For player age, both methods align closely because the distribution is symmetric. The IQR flags 117 veterans over 31 years old, while the stricter Z-score isolates 33 extreme veterans. For player salary, we see a massive discrepancy. The IQR method flags 388 financial outliers making over $4.39 million. In contrast, the Z-score method only catches 74. Because a few massive superstar contracts heavily inflate our standard deviation to 4.69 million, it pushes the Z-score boundary out, making it far too conservative. And actually, this gap perfectly proves the extreme economic inequality in the league. Moving on to the probabilistic behavior of our data, we wanted to know, are a player's age and salary tier completely independent? To test this, we used a multiplication rule test. If they were independent, multiplying the probability of being young by the probability of having a high salary would equal our true joint probability. As you can see, the numbers don't match. More importantly, look at the conditional probabilities. A veteran has a 41.3% chance of landing a high-tier contract compared to just 12.6% for a younger player. That's a 3.3 times higher odds ratio, demonstrating a clear financial premium on experience. Next, we wanted to bridge descriptive stats into inferential territory. To do this legally with such data, we verified the central limit theorem. We simulated 1000 Monte Carlo samples with a sample size of 4D in RStudio. As shown in the graphs, even though the raw salary data was heavily right skewed, the sampling distributions for both age and salary converge into beautiful, clean bell curves. Furthermore, our empirical standard errors match the theoretical calculations almost perfectly, with an error margin of less than 0.6%. This mathematically validates all the parametric inferences we will make next. With the central limit theorem verified, we constructed confidence intervals to establish our population estimates. Here, we highlight the classic engineering trade-off between precision and certainty. For player age, our point estimate is 25.59 years, moving from a 95% to a 99% confidence interval, widens the range slightly to ensure higher certainty. For salaries, the 95% interval estimates the true mean cap hit between $2.54 and $2.89 million. When we bump that certainty up to 99%, the interval widens from 2.49 to 2.94 million. This visualizes how stretching our certainty requires sacrificing a bit of precision.
From now I'll continue, and here we used one sample t-test where we analyzed player age and a player salary against specific benchmarks at a 5% significant level. For both cases, we rejected the null hypothesis, and for the first case, confirming that the true mean age is significantly below 26 years, and for the second case, Concluding is that the true mean salary does indeed exceed $2.5 million. In this slide, we used chi-square test of independence to see if a player's side of the ball influences their salary tier. As you can see here, our p-value came out above our alpha level, and we failed to reject the null hypothesis. Ultimately, a player's side of the ball has no statistically significant effect on their salary tier. Next, we look at regression and correlation to see how age impacts player salary across our players. Looking at our R-squared value, age alone only explains 10.6% of the variance in salary. And these are our conclusions according to what we did and what the numbers tell us. And here is our references and materials, and thank you for listening.